Step 2 gave us permission to use the normal model. It took a moment to draw one up here. We're going to insert the information from our word problem into this model. So again, the null hypothesis is assumed to be true until we can prove otherwise. So when I think about this model, it'll be centered at the value of the null hypothesis. That is the mean of this model. So again, if you remember, P was equal to 0.23. Part of its innocence is assuming it's true, thus it gets to be the middle of the model. Now, you've seen me work a few of these videos already throughout the course. You know immediately after I put the mean in, I'm anxious to figure out what the standard deviation is. Since this has to do with a sample, we're going to use the sampling distribution for proportion standard deviation here. So that's P times Q all over N. That should look familiar from a previous lesson. So let's insert what we know. P is 0.23 times Q, 0.77. And we're going to divide it by our sample size, which was 120 crashes. Now, if you throw this in your favorite scientific calculator, you will see that this is approximately, out to 3 decimal places, 0.038. That is our standard deviation. What I'm going to do next is tick off 3 equally spaced marks here and label this model to its full extent. So if I add 0.023 here, I get 0.268. If I add it again, I get 0.306. One more time for the third tick mark. If I add 0.038, I get 0.344. I'm going to do the left side as well. If I subtract 0.038, I get 0.192. Again, 154. Subtract 0.038 for the third time, I arrive at 0.116. So this is how we would expect samples of size 120 to vary if P is equal to 0.23. So this is our model. This is the model we're ultimately going to use to see how different our sample proportion is from this, also quantify a probability, which is really cool. So notice I haven't talked about p hat at all during this whole testing process. It's only until this moment in step 3 that I come in and I take the sample evidence that the community group collected, and that was 38, if I remember, crashes involved cell phone use over 120. And again, dividing that out with my handy scientific calculator, I would get, let's see, 0.317. This is what they observed on their roadways. This is their evidence. So let's see how this evidence fits into a world where 0.23 or 23% is the proportion that have cell phone use involved. So if I look at the number line, I see that 0.317 falls right about there, just guesstimating. And I'm going to shade to the right. This is called a right-tailed test. So when the evidence is put in, and our alternative, if you remember, was P is greater than, then we shade to the right. So what we have here are a few things we're going to use to see if we should keep the null or maybe reject the null. So what I want to point out first is that if I think about how many tick marks the way it is 1, 2, and a little bit. So Z, remember Z counts standard deviations, is certainly greater than 2. So that's the first thing that makes us go, this value seems extraordinarily larger than the 23% we know nationwide. So this is starting to make me think. This is an unusual finding according to what we know about the nation. Also, what I have in red here, so the Z, the green just counts the tick marks. This is our Z-score. We'll see when we get to software, it's called Z-stat, and it's going to do a lot of work for us, but I do still like to sketch these things out. What this is here that I've kind of done a crisscross shading with, this is what we're going to call our probability value. And I want to apologize in advance. They've shortened this to p value. Still probability, but for short they call it p value. So we're going to also be able to judge if this is an unusual finding, not just by the proximity of the data to the middle of the distribution, but also by a probability. How likely would it be for us to observe something this size or larger given the null hypothesis is true? Now that second statement I said, given the null hypothesis is true, that's that assumption that we had in the beginning. Given the null hypothesis is true, how unusual is this? For me, this seems extremely unusual.
I'm going to show you the few quick steps it takes to solve this problem in StatCrunch. So we'll first click on Stat, Proportion Stats, one sample. We only had one sample. And we received not raw data, but the summary. So this feels familiar. It's going to start asking us a few questions. First, it asks for the number of successes. So in our problem, 38 of the car crashes involved cell phone use. There's our number of successes. Our number of observations, 120 car crashes were examined. So basically, the StatCrunch is asking you for p hat, but it wants it in pieces. It wants the numerator of p hat and the denominator. The default setting is on hypothesis testing for a population proportion here. P is already there because we went through proportion stats. So we're just going to edit this and change it to our 0.23. Notice it repeats itself below because it knows these two numbers have to be the same. There's strict equals to there that's already set for the null hypothesis. The alternative hypothesis is going to be greater than. We were doing a right-tailed test. So we've given it the evidence, we've told it the hypothesis. The next thing we have to do is hit compute. Here's our output. It reminds us of what we told StatCrunch our hypothesis statements say, so you might want to glance at those to make sure that they were entered correctly. We get our count, our total. There's our sample proportion, 0.317, that we used when we sketched it out. But what we're most concerned with are these last two columns. This is our Z-stat, or Z-score, and we were able to tell from our sketch that it was more than 2. Specifically, our Z-score is 2.26. And our p-value is 0.012. So that is basically how many tick marks to the right our p-hat was. And again, what was this shaded area to the right? And again, a very small probability here at 0.012.